The universe is a vast and ever-changing canvas, a cosmic masterpiece that stretches beyond our wildest imaginations. It is filled with stars in various stages of life, each one telling a unique story of creation, existence, and eventual demise. Some are bright and young, burning with intense energy, illuminating the cosmos with their brilliance and vigor. Others are nearing their end, their fuel dwindling, their light fading as they prepare to transition into the next phase of their existence. But what happens when a star completely exhausts its fuel, when it has given all it can to the universe? The answer lies in the concept of black dwarfs, the theorized final fate of many stars, a state of ultimate stillness and silence. Black dwarfs are not yet a reality. They remain a theoretical construct, a glimpse into a future that is billions of years away. The universe, as we understand it, is not old enough for them to have formed. It is still in its relatively youthful stages. However, their theoretical existence provides us with a glimpse into the distant future, a time when the universe will be a very different place. It allows us to contemplate the ultimate fate of stars like our own sun, which will one day exhaust its fuel and transition into a black dwarf. Imagine a cold, dark remnant, a stellar ghost barely perceptible against the backdrop of space, a silent witness to the passage of time. This is the eventual destination of countless stars, including our own, a universe filled with the quiet remnants of once brilliant suns, marking the end of an era in the cosmic story. A black dwarf is essentially a white dwarf that has cooled down completely. It no longer emits any significant heat or light. Picture a massive object, roughly the size of Earth, but with the mass of our sun. This object is incredibly dense. It is composed mostly of carbon and oxygen, the remnants of a star's core. Black dwarfs represent the final stage in the evolution of many stars. They are the end of the line in a long process of stellar transformation. Understanding black dwarfs, even though we haven't observed them yet, gives us a deeper understanding of the life cycle of stars. It also allows us to contemplate the ultimate fate of our own solar system. Stars form from massive clouds of gas and dust called nebulae. These nebulae are often the birthplaces of stars, where the raw materials of the universe come together to create new celestial bodies. The process begins when regions within these clouds experience slight disturbances, which can be caused by nearby supernova explosions or the gravitational influence of other stars. These clouds collapse under their own gravity. As the gas and dust particles draw closer together, their gravitational attraction increases, accelerating the collapse. This process can take millions of years, gradually transforming the nebula into a dense, spinning disk of material. As they collapse, the material at the center heats up. The increasing pressure and temperature cause the core to glow brightly, signaling the birth of a protostar. This early stage of star formation is crucial, as the protostar continues to gather mass from its surroundings. This eventually reaches temperatures high enough to ignite nuclear fusion, the process that powers stars. Nuclear fusion involves the merging of hydrogen atoms to form helium, releasing vast amounts of energy in the process. This energy radiates outward, providing the light and heat that we associate with stars. For most of their lives, stars exist in a state of equilibrium. This balance is achieved when the outward pressure from nuclear fusion counteracts the inward pull of gravity. During this stable phase, stars can shine for billions of years, depending on their mass and composition. The outward pressure from nuclear fusion balances the inward pull of gravity. This delicate equilibrium ensures that the star remains stable, neither collapsing under its own weight nor exploding outward. However, the star's life cycle is far from over. This balance cannot last forever. As the star ages, it exhausts its supply of hydrogen fuel in the core. This marks the beginning of the end for the star's stable phase, leading to dramatic changes in its structure and behavior. Eventually, a star will run out of fuel for nuclear fusion. When the hydrogen in the core is depleted, the core contracts and heats up, while the outer layers expand and cool, transforming the star into a red giant. When this happens, the star's core begins to contract under its own gravity. The intense pressure and temperature in the contracting core can ignite further fusion reactions, creating heavier elements like carbon and oxygen. For stars like our Sun, this process results in the formation of a white dwarf. A white dwarf is an incredibly dense remnant, roughly the size of Earth, but with a mass comparable to the Sun. The outer layers of the star are expelled into space, forming a planetary nebula. This beautiful and colorful shell of gas and dust glows brightly, illuminated by the remaining heat of the white dwarf at its center. The white dwarf, no longer supported by nuclear fusion, slowly cools down over billions of years. As it radiates away its remaining heat, it gradually fades, becoming less and less luminous. This cooling process will eventually lead to the formation of a black dwarf. A black dwarf is a theoretical stellar remnant, so cold and dark that it no longer emits any significant heat or light, marking the final stage in the life cycle of a star like our Sun. The reason we haven't observed any black dwarfs yet is simply a matter of time. The universe, at an estimated 13.8 billion years old, is not old enough for any white dwarfs to have cooled down completely. The cooling process for a white dwarf to become a black dwarf is incredibly slow. It is estimated to take trillions of years, far longer than the current age of the universe. This fact highlights the vast scales of cosmic time. The processes that govern the universe operate on timescales that dwarf human comprehension. While we may not be around to witness the formation of the first black dwarfs, their theoretical existence allows us to appreciate the immense timescales involved in stellar evolution. Section 5. The Invisible Giants, Envisioning Black Dwarfs. Imagine a sphere roughly the size of Earth but incredibly dense, containing the mass of our Sun. This sphere is cold and dark, emitting no significant heat or light. It drifts through the vast emptiness of space, a silent relic of a once bright star. This is what a black dwarf would look like if we could observe one. However, because they emit no light of their own, black dwarfs would be incredibly difficult, if not impossible, to detect directly. They would be incredibly faint, lost against the backdrop of other celestial objects. Their existence would only be revealed indirectly, perhaps through their gravitational influence on surrounding objects. Section 6. Frozen in Time, the Silent Heart of a Black Dwarf. Inside a black dwarf, all nuclear reactions have ceased. The atoms are locked in place, unable to undergo the fusion processes that once powered the star. The black dwarf exists in a state of almost perfect stillness, its internal structure frozen in time. However, even in this state of near absolute zero temperature, some theoretical quantum processes might still occur. These processes, such as electron degeneracy pressure, would prevent the black dwarf from collapsing further under its own gravity. This highlights the complex interplay between quantum mechanics and gravity, even in the seemingly inert environment of a black dwarf. Section 7. The Universe's Twilight Years. Black dwarfs, if they exist as theorized, will play a significant role in the universe's ultimate fate. As the universe continues to age and more stars reach the end of their lives, black dwarfs will become increasingly common. They will be the dominant type of object in the universe, outnumbering all other celestial bodies. This era of black dwarfs represents a bleak and desolate future for the universe. With most stars extinguished and the universe shrouded in darkness, it marks a significant departure from the vibrant and active cosmos we observe today. The universe, once filled with the light and energy of stars, will become a cold and dark place. Section 8. A Glimmer of Hope. The Potential for Reignition. While black dwarfs are generally considered to be the final stage in the life cycle of stars, some theories suggest the possibility of reignition. These theories propose that under specific circumstances, the material in a black dwarf could be compressed enough to reignite nuclear fusion. One such scenario involves a collision between two black dwarfs. The immense pressure generated by such an event could potentially trigger a runaway fusion reaction, briefly bringing the dead stars back to life. However, these events would be incredibly rare and highly speculative. Section 9. Finding the Unfindable. The Search for Black Dwarfs. Detecting black dwarfs directly is a daunting task due to their lack of emitted light. However, astronomers are exploring indirect methods to search for these elusive objects. One promising approach involves gravitational lensing. Massive objects, like black dwarfs, can warp the fabric of space-time. This warping can bend the light from distant stars, creating a lensing effect. By carefully observing these lensing events, astronomers might be able to infer the presence of a black dwarf. Section 10. Echoes of the Past, Whispers of the Future. Black dwarfs, although theoretical, offer a profound perspective on the life cycle of stars. and the evolution of the universe. These stellar remnants are the final stage in the life of a star, a stage that our universe has not yet reached. The concept of black dwarfs pushes the boundaries of our understanding, challenging us to think about the distant future. They serve as a reminder of the impermanence of even the most massive and energetic objects in the cosmos. Stars, which shine so brightly for billions of years, will eventually fade away, leaving behind these cold, dark remnants. This process is a testament to the ever-changing nature of the universe. Their existence, while still unconfirmed, underscores the vastness of cosmic time and the incredible processes that govern the universe. The timeline of the universe is filled with events that span billions of years, and black dwarfs are a part of this grand narrative. They remind us of the slow yet relentless march of time. As we continue to explore the universe and refine our understanding of stellar evolution, the search for black dwarfs will undoubtedly continue. Astronomers and scientists are constantly on the lookout for evidence of these elusive objects, hoping to catch a glimpse of the future of our universe. These elusive objects hold the key to unlocking further secrets of the universe's past and its ultimate fate. By studying black dwarfs, we can gain insights into the final stages of stellar evolution and the long-term future of the cosmos. They serve as a reminder that even in the darkness, there is much to be learned about the cosmos. The universe is full of mysteries waiting to be uncovered, and black dwarfs are just one piece of the puzzle. As we look to the stars, we are reminded of the endless possibilities that lie ahead.